feedback, shift registers, introduction, and the big picture. Hello and welcome. Today, we are exploring a specialized digital tool designed by the students of Puducherry Technological University, the Virtual Laboratory for Linear Feedback Shift Registers, or LFSRs. In the world of digital communication, randomness is paradoxically vital. Whether it's encrypting a message or testing a circuit, we need sequences that appear random but are strictly controlled. This virtual lab, built using HTML, CSS, and JavaScript, provides an interactive environment to visualize, simulate, and master these pseudo random sequence generators. What is an LFSR? Theory and mechanism. So, what exactly is an LFSR? At its core, it is a shift register whose input bit is a linear function of its previous state. The most common function used is the exclusive OR or XOR operation. The system consists of three main components. First, a series of flip-flops that store the binary bits. Second, XOR gates that create a feedback loop. And third, a clock generator that pulses the system to shift bits from one stage to the next. The feedback is determined by taps, specific positions in the register that are picked to be XORed together. This feedback bit is then fed back into the first flip-flop, while the last flip-flop produces the output bit. This loop is what allows a simple circuit to generate complex, repeating patterns. The importance of the seed. Every LFSR starts with an initial value called the seed. Think of this as the DNA of your sequence. There is one golden rule in LFSR design: the seed must never be all zeros. Why? Because the XOR of 0 and 0 is always 0. If a register hits an all 0 state, it becomes locked. It will simply stay at 0 forever, and the sequence generation will fail. To prevent this, the PTU virtual lab allows you to manually enter a non-zero seed or use a randomize feature to ensure the system initializes correctly. The seed dictates where the sequence starts, but the taps dictate how long and complex that sequence will be. Performance, math, and limits. In terms of performance, LFSRs are prized for their high speed and low power consumption. They are incredibly efficient because they require minimal hardware resources. Mathematically, the length of a sequence is determined by the width of the register, denoted as n. The maximum number of unique states an LFSR can produce before it starts repeating is 2 to the power of n minus 1. For example, a 4-bit register can produce a maximum of 15 unique states. However, there is a catch. If you choose the wrong tap positions, the sequence might repeat much earlier than the mathematical maximum. Finding the proper taps is a key part of the experimentation process in this virtual lab. Applications and security trade-offs. Where do we use these in the real world? LFSRs are the backbone of hardware testing through built-in self-tests or BIST. They are also used in data scrambling, error detection like CRC, and spread spectrum communication systems like CDMA. However, they aren't perfect. Because LFSRs are deterministic, they are predictable. If an attacker knows the tap positions and a small part of the output, they can mathematically reconstruct the entire sequence. This makes them unsuitable for high-level cryptography if used alone. The strength lies in speed and simplicity, not in absolute, unbreakable secrecy. Navigating the virtual lab. The PTU virtual lab is designed for deep intuition. Users can select register widths from 4 to 10 bits. Once you set your taps and seed, you can hit the run button to see the sequence generate in real time. If the movement is too fast, you can use the step function to advance one clock pulse at a time or adjust the speed slider to slow down the visualization. The lab even provides a live waveform generator so you can see the digital signal as it's being created. Once your experiment is complete, you don't have to just look at it. You can click the Export CSV button to download your state table for further analysis. Whether you are a student or an engineer, this tool simplifies the complex behavior of digital logic into a clear, visual experience. Thank you for joining us in the virtual lab. Happy simulating.